Okay, hi and welcome to video notes on finding differences. So let's get that straight. What does that really mean? That's kind of our process of what we're going to go through is finding differences. But what's our goal is really what we should talk about here. Our goal for this whole entire unit and really the whole year of algebra has been working up towards this. Our goal then is to take real data, which we just started to peek at last unit, and start to model it with a function that's an actual math function. So we're going to take real data that could be all over the place, and we're going to try to see if there's a model that'll fit it so that we can make predictions and say, hey, this is what's going to happen per our model. So that's our goal. Remember, everything we're doing today is really all review. We've seen this in our previous units somewhere. So we're going to go through this. Now, what does it mean to find a difference? Well, let's say that you're given some set of data. I don't care what kind of data it is. I don't care how big it is, but you've got data, meaning two variable data. You've got an x coordinate and a y coordinate, two things that we're going to correlate together. And we'll talk more about correlation in a bit. But let's say that this is a set of data we've got. Right now, we're not going to pay attention to what they mean. We're going to leave that for a later note. Today, we're just going to focus on how to write a model for some basic data. Okay, the first thing that you want to go through is try to find the first difference. So there's going to be two differences that we're going to take, and then what we call a common ratio we're going to try to find, or a geometric difference. We're going to try to find that through the data. So there's going to be three things that we have to look for. So let's start with the first one that you should always do. But before we do that, let's talk about what we should do in the overall process, because that changes just a bit. How to write a model in general for any set of data. The very first thing we should do is graph the points. This is a visual process. We're trying to take data that looks like these little purple dots, and I'm adding blue ones in here, right? These little dots. And we're trying to make a model or a line, right? A model is a function, and the function are the y values that cross the x values, and they should go in the middle of those as best as possible. That's what I mean by writing a function for a set of data, or modeling. So it's important that you look at this data. Plot the points. You can do it on your calculator, you can do it by hand, you can do it in Desmos, but plot it, look at it, because 9 times out of 10, you're going to be able to see what it looks like and say, oh, that looks like this function. I mean, if it's all in a straight line, it's linear. If it looks like a quadratic, it's quadratic. You get the idea? After that, we'll go ahead and start taking our differences. And then we're going to use what we know about for functions to write the actual function model for that. All right, so now that we've got that cleared up, let's take this any old data that we've got and take the first difference. So the first difference then means to take y2 minus y1. So I'm going to take y2 minus y1, I'm going to get negative 2. And I'm going to do it again from 0 to 2, and I'm going to get negative 2, and that's going to be all the way down the sequence. If it's the same, or what we refer to as constant, if that first difference is constant, which this set of data right here is, we're done. That was pretty easy. What does it mean, though, now that we have this constant first difference? It means that it's a linear function. Okay, so if the first difference is constant, you're done. You've identified it as a linear function. But let's be a little bit more specific here. Look at this. This data has a constant rate of change. That's a term we use with linear functions, remember? So if I go from 4 to 2 to 0 to negative 2 to negative 4, you can see the movements all down by negative 2. That's what you're seeing. By taking the first difference, you're seeing the constant rate of change. Better yet, ready, you get the slope, remember. So that ends up being the slope. So you have one piece of information for writing a linear function. So what does a linear function look like? We can write it into y equals mx plus b, or we can even write it into y minus y1 equals slope times x minus x1. Do you remember what that's called? Slope-intercept, or point-slope form, correct? So you can choose either method to write it into. So now that we've got the slope, we've already identified that, we need to find, if we're using at least the first one, right, we need to find one more piece of information, which is the y-intercept. The y-intercept is usually known by the fact that it has a 0 coordinate for the x value, which you can see is right there. So my y-intercept for this one is visible in the table. Sometimes it's not. And if you wanted to use this method here, the slope-intercept method, you'd have to calculate for the y-intercept. Or, if you were super good, you would plug it into the point-slope form and take any other point from the table. It doesn't matter which one. Just pick one of them, use the x value where the x value goes, and the y value where the y value goes. And you'll be all set. Well, I should say y1 and x1. So, but we have the y-intercept already. It's equal to 0. We've got all the information we need to write the model for slope-intercept form. So let's go ahead and do that. Y equals my slope, which is negative 2, times x plus 0, which I'm not going to write because it's 0. So let's mark this down that that's a linear function and check that off our list. Now we remember how to write a model for a linear function. So let's scooch in here a bit and let's check another set of data. Okay, so we're going to look at this data. We're going to try the first difference. We're going to probably notice right away that this is not moving by a constant rate of change. I'm going from 5 to 4, which is -1, 4 to 5, which is +1. So that already makes me feel weird. Then 5 to 8 is by 3, and then 8 to 13 is by 4. So I'm feeling weird about it being a constant rate of change. I do have to stop here and make a note. This is perfect data. All of the stuff we're going to do here. Okay, and the reason that I'm going to tell you that this is perfect data is that everything we're going to do will match a model function exactly. Eventually, we're going to move into actual random data, stuff that you would get from real life. This process still works, but it's not as neat and clean. Okay, so now that I've said that, let's go back to this. Let's go ahead and take that first difference. So from 5 to 4, or y2 minus y1 is going to give me a -1. And then continuing that process from 4 to 5, I'm going to go to +1. From 5 to 8, I'm going to go to 3. And 8 to 13, I'm going to go to 4. So that's not constant. I'm going to write it so that you see that that's not constant. Okay, which means that I have to do something else. It means that it's not linear data. So now I'm going to go ahead and move and take my second difference. Taking a difference of a difference, or doing the same thing I did, but doing it to these differences that I just took. That's what I'm going to do. If this is constant, well, let's talk about what it actually is first. If I go from -1 to 1, I'm moving from -1 to 0 to 1. That means I'm changing a +2. And from 1 to 3 is +2, and that should be a 5. And from 3 to 5 is also +2. Those are all 2's. If that's constant, and it is, okay, if that's constant, then what we find out is that this is a quadratic function. Okay, now we can start to write a quadratic model for this data. Again, this is perfect data, so it'll work out really nicely for us. So here is the general form for a quadratic function. F of x equals, ready, ax squared plus bx plus c. Right? That's the one that we can write into pretty easily. We could write into, if we wanted to, vertex form, which would be a times x minus h squared plus k. In that case, we'd go a little bit different of a route. We'd need to find the vertex, which we could easily do if we could see it in our table. So I'm just going to point that out now. I'm not going to go that route, but I'm going to point it out that you could see the vertex right here. This would be the vertex, noticing that the symmetry, and then we don't have a lot to work from, but I'm noticing that my y value being 4 goes to 5 on both sides. There's the symmetry in that. So you could have the vertex right there and call it a day. Okay, you could find I'll show you how to find the a value in 1 second. Oh, let's fill this in. Second difference, equals constant means quadratic. That's what we want to write there. All right, so let's go ahead and try to write this into standard form, because a lot of us will approach this way as well. So if we need to find standard form, we're going to first find our y-intercept if it's visible. And you can see that I pre-highlighted the y-intercept here. It's 0 and 5. How do I know? Because my x value is a 0. So that's my y-intercept. So that means in this form that c equals 5, because that's your y-intercept in this form. Okay? Remember, that is not the y-intercept for k if you're going into vertex form. All right, so now that we've got that down, let's see what pieces we've got so far. So far we've got the c value. We know that's 5. But we also need to find, for this one here, right, the standard form, we need to find b and a. Well, a can be found by a quick calculation of taking the second difference, the constant second difference, which is 2, and we divide it in half. So we're going to take 2 and divide it by 2, which is going to give us 1. So we found a now. The one piece that we don't have is b, so we need to find b. We're going to have to calculate for b. So we're going to take any other point. I'm going to pick this one here in green, and I'm going to plug it in to all the parts here, plus I'm going to plug in c and a, and the only thing left that I won't know is b. And then I'm going to calculate to find b. So let's plug that in. F of x is my y value, so that's going to be 4. And let me change my color here so you can see that. So it's going to be 4, and then my a value is 1, and my x is going to be -1, it looks like, from my random point, squared, plus my b, which I don't know. My x is still -1, and my c value is 5. So now I'm going to do this calculation and figure it out. So -1 squared is 1. 1 times 1 is 1. So I get 1, negative 1 times b is negative b, and plus 5. So I'm going to subtract that 5 to the other side. That's going to, well, actually, I'm going to probably put these two together, which is going to make 6. And then I'm going to subtract that 6 to the other side. So I'm going to get negative 2 equals negative b, and then I'm going to reverse that. So I'm going to find out that b is equal to 2. So if I go to write the model for this, I'm going to take all my pieces, my c, my a, and now my b, and I'm going to write it in here, replacing a, b, and c. So f of x is equal to x squared plus 2x plus 5. All right, and then I've got my model. All right, let's move down and do one more, which is this set here. Now, this is a horizontal table. That makes no difference, by the way. We're allowed to work vertically or horizontally with a table. Here's my x values, here are my y values. If you feel really crazy about it, turn it into a vertical table. That's fine. But in this one, what we're going to do is we're going to look right now first, and we should have plotted these points. I did skip that step on all of these. I do apologize. Did that for time. So I'm going to look at these y values, and I'm going to notice they're not changing linearly. So I know that that's not going to be a first difference, a constant first difference. I'm going to tell you for time's sake that if I took the second difference, it also would not be constant. So what we're going to come to is we're going to check the third method, which is by the common ratio. Okay? The common ratio says that we're going to take y2 and divide it by y1. So now we're doing a division versus a subtraction. So I'm going to go ahead and subtract those points. I'm sorry, divide those points, and what I'm going to come up with is if I take 20.25 and divide it by 13.5, I'm going to come up with a value of 1.5. And if I do that through the table, and you can check on your own, you can pause the video, but that's going to come up to be 1.5, and it's going to come up to be constant. If that's constant, right, taking the geometric difference of these, right, so dividing them, if that's constant, we find out that this is an exponential function. Okay, so now that we've got an exponential function, let's try to write the general form of it. Y equals a times b to the x. That's the general form for an exponential function. So there's only two pieces that we need to find, a and b. Well, guess what? You've got one of them. One of them is your common ratio here. The value that comes out, this constant value, that is your b. Oops, I didn't write. So we've got our b. So the only thing we need to find is our a value now. Now, the a value can be a little tricky for exponentials. The easiest way to address this is to go backwards in the table until you get to 0. So I want to move this table backwards. Well, if I'm multiplying by 1.5 to go forward, then to go backwards, I need to divide by 1.5. So if I do those divisions, if I take 13.5 and I divide it by 1.5 to go back to the second term in this sequence, I'm going to get 9. And if I do that division again by 1.5 to 9, I'm going to get 6 for the first term, and then the last term, or the initial value, is going to be 4. So what I found was my y-intercept by working the table backwards. That's probably the easiest method to go through. So now that I've got my a at 4, I can write my function. So y equals 4 times 1.5 to the x power. And that would be the model that would model this data here. Again, in class we'll see some of these, but right now we're just speeding through the process on how to do this. So the notes are done. What I did on the next page here, and I also made sure to write this out. Oops, let's do that a little bit bigger here. That didn't click. There we go. Make sure that you graph and look at first, because a lot of times you can go straight to the method that you have to do, and you don't have to do the first difference, the second difference, and the geometric. You can kind of see which one you need to get to. So make sure that you graph the points, and look at them. Okay, so this is just a quick summary of each of those methods to kind of walk you through. First difference, it tells you if that's constant, this is how you do it, exact process that we just went through. Same thing for the second difference, and also for the exponential and how to write it. Again, visually, this is what we'd be looking for points on a graph. If they lined up, if they were quadratic in some fashion, or exponential. Remember, exponential has a really steep curve. It goes really, really slow at first, and then it should have a really steep curve. So, thanks for watching my notes. We'll see you in class.